Do 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 do. Mm-hmm. Mm-hmm. Ooh, 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 ooh. La da 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 da. La da 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 da. La da 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 da. Hey, do you remember Professor Huang's class, the coolest science experience ever? Totally, I'd like to think I can remember everything. Haha, imagine that. Well, you could too. You can do anything you put your mind to. Remember when we learned about ibutilide, or chemical name Corvert? Wow, that's so cool. I totally remember. You must also remember that ibutilide has invisible H atoms attached to carbon atoms through intramolecular force, right? Of course, and it could also form hydrogen bonds with water and intermolecular force, and that's because the hydrogen bond is between two separate molecules. You're really smart. Thank you. My credit goes out to Professor Huang for always making class so interesting. Whoa, look at that. Whoa, is that a kite? No, silly, it's a butylide. You can see the hexagonal chamber and stairs of carbons that we know will be attached to invisible H atoms. You're right. I'm sure if we get a closer look, we'll be able to see some of the other molecular geometry from the Vesper theory. You betcha. There's trigonopyramidal, which is a central atom with a lone pair with 3 bond attachments. Let's take a closer look and see what we can find. I don't think we can reach that high. We can, you just have to believe. Okay, I trust you. Let's go for it. Whoa, I can't believe we have a butylide now, and I was able to bring it back to my lab. I know, that's so cool. What else do you remember about a butylide? Let me grab a pencil so I can show you the expanded structural formula of a butylide. That way it is easier to imagine the hydrogen bonds with water that our drug could have. While I do though, a butylide is a class 3 drug, a part of the antiarrhythmic. It represses irregular beats of the heart, and that's what most class 3 drugs do. They're potassium channel blocking properties, which all control the signal of the heart. But back to the molecular geometry. It's important to note that each carbon with an intramolecular bond has 4 bonds. So we can't see 4 bonds attached always, but we can assume the invisible H bonds are a factor. Oh, nice. Does octet stability apply? Great question. It definitely does. That builds off the carbon-hydrogen bonds we previously talked about, even with other atoms. This nitrogen, for example, has 3 single bonds, each bond holding electrons. Therefore, we know to add a lone pair for octet stability, which is really just 8 happy electrons vibing together around one atom. Wow, that's cool. You think that's cool? Look at the molecular geometry based off the Vesper theory. Let me go over some more background info while I finish up this illustration. So, as we mentioned, ibutilide has its primary use for repressing heartbeats. In other words, just slowing down a heartbeat that cannot function at a normal rate. And there are a few other drugs that work with the same effect, so it's worth noting that class 3 antiarrhythmic drugs should not be taken within a few hours of each other. The lily of the valley, for example, is one of these drugs, and there are some that can be taken as far as 24 hours apart. So it's always good to check with a trusted health official. Yeah, so there's that. Wow, that's really interesting. I love hearing about ibutilide. Yeah, back to the Vesper theory though. Here we can see tetrahedral bonds because there's a central atom with 4 single attachments to it. And this little stair effect allows us to make some conclusions or assumptions that the molecular geometry is going to be similar, at least where we see these stairs of carbon-hydrogen bonds. And then there's even some up here at top. We can see 3 of the ghost hydrogen bonds attached to our central carbon atom. Yeah. As we mentioned before, the nitrogen with the lone pair is trigonal pyramidal, so we just have to look for other central atoms with the same characteristics. Ibutilide doesn't have too many, so there's one more up top underneath our sulfur. And lastly, ibutilide has some trigonal planar bonds, and those are similar to the pyramidal bond, but easier. Oh, nice. I like easier. The only difference is that the trigonal planar does not have a lone pair. It has 3 single attachments. If we look at the hexagonal chamber, we can see 6 different trigonal planar bonds. Thanks for all that info. Wait, there's more. We can now form hydrogen bonds with water since you have a better understanding of the intramolecular and intermolecular bonds. Let me draw out some water molecules for our illustration. As I do, though, I want to go over some of the rules and background on H bonds, which is just an intermolecular force. And by intermolecular, I mean it's a bond between 2 separate molecules. So, when forming H bonds, it's important to remember there are both bond acceptors and donors. A bond acceptor would be a hydrogen attaching to a central atom with a lone pair within the given molecule. The donor is one that a hydrogen is already attached to the molecule, and it needs an outside negative charge. Oh, okay. It's important to note the electronegativity and IMF for hydrogen bonding. And it's really important to remember that hydrogen bond acceptors must have an intramolecular bond, which means within the same molecule, an intramolecular bond with either a nitrogen, oxygen, or fluorine, or for short, NOF. And they must be making the intermolecular force with one of those same 3 atoms. Now I'd like you to take a look at the possible hydrogen bonds with water that can take place with the butylide. So our very first one, I'll use red lines to indicate the bent bonds, intermolecular bonds that occur. Our first one is a acceptor because the oxygen is attaching to an outside molecule where it receives its hydrogen. Beneath that is a donor, and I'm sure you guys are aware that is because an outside oxygen from our water molecule is attaching to a hydrogen inside of a butylide. Beneath that, our trigonal pyramidal, the nitrogen is an acceptor bond because it is attaching to a hydrogen from the water molecule. Beneath that, at our other nitrogen, we can accept the same thing. It is an acceptor attaching to a hydrogen from our water molecule. Over to the right side, if we look at the bottom, there's a hydrogen attaching to an outside oxygen, and we can assume that is going to be a donor. Just above it is an oxygen attaching to an outside hydrogen, the reverse. So that is an acceptor. And since you made it all the way to the end, may as well see the last one. It is an oxygen attaching to an outside hydrogen. So that too is an acceptor. Wow, that's so cool. Yeah, it really is. There's a lot to learn from the Vesper theory, and it goes all the way to hydrogen bonds, IMFs, and much more. Did you also know that you can find the molar mass of a butylide by taking a look at the periodic table and adding the mass of each element to each other? It comes out to 384.583 grams. Allow me to illustrate where on the periodic table exactly you can find the mass for each given element. If you look at this element here, hydrogen, we see at the bottom there's the element mass of 1.00. Some results may vary. And then next to it, there's an electronegativity chart, which sometimes the periodic table provides. And this time, the numerical value is going to be at 2.1, And we can use this to remember polar bonds versus nonpolar. Anything with a 0.4 to 1.7 electronegativity difference is going to be nonpolar. And in this case, a butylide only has nonpolar bonds between hydrogen and carbon. That's awesome. Do you know how many milligrams of a butylide are contained in 2.0 milliliters of a 3% solution? Yeah, we just do mass solute divided by the volume of the solution multiplied by 100%, which ends up being 0.060 grams. Dang, that's cool. Yeah, well, one last thing. PubChem says the solubility of a butylide is 100 milligrams per liter, so it could be inside of a glass of water, and we'd never know, as long as it wasn't saturated.